students. Now, today in continuation of the thermodynamics, we are going to do further. In yesterday's class, we have done up to the first law of thermodynamics, and the first law of thermodynamics was the energy of an isolated system is constant. Now, coming to its applications. Now, when we talk about the applications, the first application in this case is a work. Basically, this particular application we called it as a pressure in the case of gases as a pressure volume work. To understand this pressure volume work, or you can say that mechanical work, we take an example. Like, for example, this is a cylinder. Over here, we have kept a piston. Okay, now let's understand the pressure volume work. What I have done over here, we have taken a cylinder. Cylinder is being taken, and in this cylinder we have the 1 mole of the ideal gas with a frictionless piston. The red colored which I have made, it is a frictionless piston. Now the total volume of the gas over here, I say that it is a VI, means volume at the initial stage, and the pressure of the gas inside is the P. If external pressure is being applied, now what I am doing, I am applying a external pressure. When you are going to apply a external pressure, say suppose Px, so what is going to happen? This external pressure is greater than the P, that is your pressure over here. So piston is going to move inward. Now look the position of the piston over here and the position of the piston over here. So this piston is going to move in the inward direction till the pressure inside becomes equal to the Px. Means these two pressures are going to become the equal. So in this case, what we do, that we achieve, or you can say the final volume over here, we get the Vf. Now during this compression, when you are putting a external pressure, during this compression, suppose the piston is going to move with a distance equal to L, and the area of the cross section of the piston is going to be A. So what will be the volume? The change in the volume is going to be equal to L into A. And when we talk about the change in the volume, that is delta V, it is going to be volume final minus volume initial. And we know that pressure is equal to force upon area. Therefore, the force on the piston, when we talk about the force on piston, it is equal to the Px A. Now, if the work is going to done on the system, again I'm repeating, if the work is done on the system by movement of the piston, then your work done is going to be equal to force into distance. This force we have written in this equation, P external, that is your pressure external, into, sorry, P external into your A into your distance. So work is going to be equal to Px. This AL is equal to the volume change, that is your delta V. So you can write down it over here. W is equal to minus P external Vf minus Vt. Okay. Now the negative sign which I have kept over here, it is what? It is the conventional sign for the work done, which will be positive. It indicates that if the compression work is done on the system, then Vf minus Vt is going to be negative, and the negative is multiplied by the negative, so it becomes automatically positive. Hence, sign obtained for the work done we get automatically as a positive. Now, say suppose if the pressure is not constant at every stage of the compression, but change in number of finite steps work done on the gas will be summed, so it will be equal to the minus summation P delta V. If the second condition could be that if the pressure is not constant but changes during the process, like it is going to always be infinitely greater than the pressure of the gas, then at each stage of compression, the volume is going to decrease by the certain amount, we can say dV. So, what is going to happen? In such a way, your equation will be what? That W is equal to VA VF P external dV. Okay, so this is a simple application, that is your pressure volume work. Now, when we get the equation that W is equal to minus P delta V, it is a irreversible isothermal process. Now, we have done that your first law of for thermodynamics, that energy can neither be created nor destroyed, but it can change from one form to the another. Now, total energy of the universe, it is going to remain the constant, or you can say ki energy of the system that is isolated from its surrounding is going to be constant. Okay. Another thing, the next terminology in this unit, we have the enthalpy and enthalpy change. Now let's understand that what is this enthalpy and enthalpy change in this case. When we talk about the enthalpy, what do you first of all understand by the enthalpy? When we talk about the enthalpy, then we say that the sum of the internal energy and the product of its pressure and volume is called as a enthalpy of the system. Okay. Now, in the case of enthalpy, we say that whatever the change in internal energy, it is going to give the heat change at for a chemical reaction at constant volume. So, constant volume pe what it is going to have? Your delta U is equal to QV. This is your what? It is a heat change at constant volume. Okay. So, but we have done that work done is equal to P delta V. So, over here, delta U is equal to QV minus P delta V. And we know that heat is equal to QP. QP means heat at constant pressure. Okay. Now, say suppose we are having a component A, it is getting converted into a component B. So, heat for the A will be HA and for it will be HB. I have told you that enthalpy is what? Enthalpy Now, in continuation to that only, we have done what? That your enthalpy is what? Enthalpy is the sum of the internal pressure, internal energy, and the product of its pressure and the volume. So, QP is going to be equal to the HP minus HA. Your H is going to be equal to U plus PV. So HA is equal to the UA plus PVA. HB is equal to UB plus PVB. So delta H is going to be equal to the HB minus HA, which is equal to UB plus P delta V, VB minus UA plus PVA. Same entities bringing at the same place plus this. So delta H is going to be equal to the delta U plus P delta V. Now your Q is what? It is the path independent. Why we are calling it as a path independent over here? Because you can say that it is a path independent, therefore it is not going to consider as a state function. But when we talk about the QP, your QP is going to call as the your it is going to call as a state function. Why it is going to call as a state function? Because it is going to depend on the path. Now after this we have the significance of the delta U and the delta H. So in this case, we say that delta U is equal to Q plus W. Means when gas is going to expand, then the work is done by the system. Means delta U is going to be Q minus W. So delta U is equal to Q minus P delta V. So Q is going to be equal to delta U plus P delta V. So in this case, we say that pressure, the process has carried out at the constant volume. So QV is equal to delta U. Now, if we say that your H is equal to U plus PV, so delta H is going to be equal to delta U plus delta PV. So in this case, we say that delta U plus P delta V plus V delta P. So what we have done? We have taken the volume as a constant and the pressure as the constant. At the pressure constant, we say that delta P is going to be equal to the 0. So when delta P is going to be equal to 0, so delta H is equal to delta U plus P delta V. Now, according to the ideal gas equation, we have done PV is equal to nRT. So, delta H is equal to what? Delta H is equal to delta U plus delta NGRT. When we say are saying delta NGRT over here, delta NG is the change in number of gaseous moles. Okay. Let's understand it with the help of example. For example, we are having the H2 gas, I2. It is going to give you a hydrogen iodide in the gaseous form. Now, what is the change in the number of the moles? Over here, we are having the 2 moles, 1 and 2. And coming to the right hand side, it is 2 moles. 2 minus 2, it is the 0. Say suppose another example, calcium carbonate, we heat it we get a calcium oxide and CO2 over here. Okay, so what is the change? Over here we have the 1 mole minus, over here what is we are having? This is in the gaseous form, this in the solid state over here. Now when we are having a solid state, so we do not consider it. We are not going to consider it. So what happens? That your change in number of moles remain as the 1 only, isn't it? Because it is the over here the one entity only. Always remember, whenever we have the solid state, we do not consider it over here. Another example is what? Hydrogen 2NH3. So delta Ng over here. These are what? There we are having the how many number of moles? We are having the 2 number of moles, isn't it? Minus over here we are having how many number of moles? 2 nitrogen and 3 oxygen over here. Oh, sorry, hydrogen we are having. Okay, so the number of moles over here, how many it has become? Just do it, solve it, and provide me the answer over here. That how many number of moles you are having, and what will be the change in the change in the number of moles. Now we say that the number of gaseous moles helps to take out the relation between the delta U and delta H. If your delta Ng is going to be equal to 0, so your delta H is going to be equal to delta U plus delta Ng RT. Means your delta H is going to be equal to the delta U. If say suppose your delta Ng is equal to delta Ng is greater than 0, then your it will be value will come in the positive, your delta H will be greater than delta U. If your delta Ng is lesser than 0, then delta H is going to be smaller than the delta U. Okay, this is about the enthalpy.